Welcome back, everyone. In this video, we will be covering the second part of Lecture 14. The topic is call options in the Black-Scholes option pricing model. Okay, let's get started. In the previous video, we learned that the Black-Scholes model is the continuous time version of the binomial model. We now want to use the Black-Scholes model to price European call options. To do this, we're going to assume the Black-Scholes assumption that stock returns are normally distributed under the risk-neutral probability measure. And we're also going to add an additional assumption that sigma is the annualized volatility of the stock, and it's constant and deterministic. And of course, we're going to be considering a stock that does not pay dividends. We'll relax this assumption in the summary slide. We want to consider a European call option on this stock with a strike of K and a maturity of T. We want to price this option. The FTAP tells us that the price of this call option is given by its risk-neutral discounted expected value, e to the negative RT, EQ of C sub T. And the Black-Scholes model is going to help us compute this expectation right here. Given the Black-Scholes assumptions, we're going to be able to make a strong computation on what is EQ-CT. Okay? If we work out all the math under these assumptions, normally distributed returns under this neutral measure, constant volatility, no dividends, then the Black-Scholes model call price is going to be given by the following equation. It's going to say that the price of the call today, C sub 0, is the difference between two terms. It's equal to S sub 0, the current stock price today, times some quantity called phi of D1, minus the present value of the strike K, times something called phi of D2, where D1 and D2 are constants given by these equations, and phi is the standard normal cumulative distribution function. It's the CDF of a standard normal random variable, or that Z table you learn about in your Stats 101 class. Okay? Note that this formula, this is the Black-Scholes call price formula, is elegant and surprisingly simple and quick to compute. It has 5 inputs: the stock price, the annualized volatility, the continuously compounded risk-free rate R, the option strike, and the maturity. And all you do is you plug these inputs into this equation, and out is going to pop the Black-Scholes call price. The main challenge is just to do the computation in the first place. The way I like to do it is do like a 3-step process where you work inside out. In the first step, what you do is you go out and you compute the two constants, D1 and D2. You take your 5 inputs, you plug them into this D1 equation, natural log of S over K plus R plus 1/2 sigma squared times T over sigma root T, and then plug that into the D2 equation. D2 is equal to D1 minus sigma root T. Okay, this part is just simple plug and chug. Okay, in the second part, in this 3-step process I like to use, you go out and you compute phi of D1 and phi of D2. These will go into more detail in the next slide or two, how to compute the standard normal, the CDF value of the standard normal random variable. Okay, but for now, we'll just accept that we compute them. Okay, in the final step, it's part 3. It's to just plug in and chug, plug and chug. Once you compute phi of D1 and phi of D2, you just multiply phi of D1 by S0, and then you subtract the present value of the strike times phi of D2. Okay, again, this is the Black-Scholes call price formula. It's very elegant and simple. It doesn't take much time to compute, and the key is just getting the computation right. Okay, and the key step that always trips people up that I've seen in the past is this second step, how to get the right values of this phi of D1 and phi of D2, because other than that, everything is just trivial. Okay, so what is phi? So phi is going to be the standard normal cumulative distribution function. It's the CDF of the standard normal distribution or the bell curve. Okay? And what the CDF is going to tell you, okay, is the area under the curve up to some value. So for any value of x, phi of x is equal to the area under the curve, under bell curve, up to this value x. Mathematically, what this is it's the probability that some standard normal random variable z is less than or equal to x, where z is normally distributed with mean 0 and variance 1. Okay? And what we're going to do to compute this phi of d1 and d2 is we're just going to set x equal to d1 and x equal to d2 in two different situations. And we're just going to compute this out. Okay? So the key is to compute this phi of d1 and d2. There are two generally accepted ways of doing this in this class. The first way is this thing called the old school method. The second way is the new school or the modern method. In the old school method, what you're going to use is you're going to use some z table from Stats 101 to compute the phi's. That is, you want to get phi of d1 and phi of d2. Okay, these are both going to be x values. You want to compute the CDF up to x. Okay, and in this old school method, what you're going to use is you're going to use this z table from Stats 101 to go out and compute the phi's. Okay, I'm not even going to waste any time going over this method, okay, because you don't want to use it. It's too time consuming. It's not used in real life. You'll never use this again after you get out of college, and you're prone to error if you use this type of method using these tables. So I'm not going to even spend any time whatsoever telling you how to do this like you did in Stats 101. What you want to use instead is you just want to use Excel or any other statistical software to compute the phi's. That is, you're going to have in the Black-Scholes equation, you're going to have the 5 inputs needed to calculate D1 and D2. You're going to calculate these out maybe on your calculator or do them in Excel, doesn't matter. And once you have D1 and D2, you want to apply this phi function on top of them to get phi of D1 and phi of D2. Okay, the way you do this in Excel is you just use this norm sdist function. So again, you open up Excel, you calculate D1 and D2, and then you want to use this norm sdist function to compute the phi values. The norm sdist function is going to take two inputs. Okay, it's got two inputs. The first input is going to be x. This is going to be either D1 or D2. You're going to plug into this input. And the second input is going to be true or false. Okay? And what you want to input into this is it's going to be true. It's going to ask, do you want to use the cumulative distribution function or not? So you put true, yes, I want to use the cumulative distribution function. If you put false, it's going to give you the probability density function, okay, the PDF, which is going to give you the first derivative of the CDF, which is not what you want in this class. Okay, and so what you want to do to compute the phi's of D1 and D2 is you want to go out, calculate them in your calculator, D1 and D2. Then you just go to Excel, and to get phi of D1, you type in norm.s.dist, plug in D1, and type in true. Hit enter. It's going to give you phi of D1. And for phi of D2, you're going to type norm.s.dist, put in D2, type in true, hit enter, and you're going to be good to go. Okay, so again, Black-Scholes call price formula. Main result that's nice is that it gives us a closed form solution for the European call option price. And if we make this assumption about normally distributed returns under the Q measure with constant volatility, formula is simple, elegant, easy to calculate, and very straightforward and intuitive. Okay, so that's a lot to take in. Let's do a couple practice problems. I'll give you a minute to read the questions and then I'll solve. The main goals of these question and the next question are going to just be to learn how to use the Black-Scholes model to plug and chug. Okay, so I'll give you a minute and then we'll work through it. So let's work through this. So the problem statement is as follows. We have Boyd Gaming. Price today of Boyd Gaming is $15 per share. Boyd is a non-dividend paying stock and has an annual volatility of 30% over the next year. Okay. Continuously compounded risk-free interest rate is 5%. Okay. And we assume there's no arbitrage and the Black-Scholes model assumptions hold. We're interested in a European call option on Boyd Gaming with a strike of 15 and a maturity of 1 year. We want to answer the following questions. Ultimately, we want to know what is the Black-Scholes price of this call option. And before that, what we want to do is we want to calculate phi of D1 and phi of D2. Solve this Black-Scholes model question. We write down our inputs. Today's price of Boyd Gaming, S0, is equal to 15. Boyd Gaming has an annualized volatility of 30%, 0.30. Continuously compounded risk-free interest rate, R, is 5%. No arbitrage, Black-Scholes model assumptions hold. We're interested in a European call option on Boyd Gaming. Strike on that call option is at the money, it's 15. Maturity is 1 year. We want to price this option. We want to price it using the Black-Scholes formula, where the Black-Scholes formula tells us that the risk-neutral discounted expected value is equal to S0 times phi of D1 minus K e to the negative RT times phi of D2, where D1 is equal to the natural log of S0 over K plus R plus 1/2 sigma squared times T all over sigma root T, and D2 is equal to D1 minus sigma root T. Okay. And phi, of course, is the standard normal distribution, that is the z-table. In the first part of the problem, what we want to do is we want to calculate phi of D1 and D2. We start by calculating D1 and D2 themselves. So we start plugging in things. D1 is equal to the log of S0 over K. S0 is 15, K is 15 as well. Plus R plus 1/2 sigma squared, so 5% plus 1/2 times 30% squared times T, which is 1, over sigma root T, 0.30 times square root of 1. What this is going to equal, you plug all this in, this is 0.317. Okay. D2 is equal to D1 minus sigma root T equal to 0.317 minus 0.30, which is sigma, times root T, which is 1. It's equal to 0.017. Okay. Next, what we're going to do is we're going to calculate phi of D1 and phi of D2. Phi of D1 is going to be equal to, we go into Excel, we type in norm.s.dist. We take D1, which is 0.317, and we type in true. Hit enter on Excel, and you're going to see this is 0.6243. Phi of D2, similarly, go out, type in norm.s.dist on Excel. Take D2, 0.017, and true. And this is equal to 0.5. You'll see in Excel, 0.5066. These are the phis we need. All you do is plug and chug on Excel, no problem whatsoever. Okay. What we want to do in the second part of the problem is then use these to price the call option. Okay. We need to plug in our inputs here. Price of the call option, as we saw before, is equal to S0 times phi of D1 minus present value of the strike times phi of D2. We know phi of D1 and phi of D2 now. All we have to do is plug in inputs. C0 is equal to S0, 15 times phi of D1, which is 0.6243, minus the present value of the strike, 15e to the negative 0.05 times 1, times phi of D2, which is 0.5066. Plug and chug here, what you're going to get is $2.13. And what we say is the Black-Scholes call price is C0 equal to $2.13. excuse me, $2.13. Okay, very easy, just simple plug and chug. Black-Scholes, a lot of math goes behind Black-Scholes. One of the most beautiful formulas in finance that'll pop out, one of the most elegant derivations too. Many ways to derive it as well. But the nice thing is that it's easily computable once we have the inputs. So we'll do one more practice problem with the Black-Scholes call price. Let you read that for a minute, and then we'll work through it. Okay. All right. So the problem statement as follows. We have MGM. MGM's stock price today is $10. It's a non-dividend paying stock with an annual volatility of 50% over the next year. Excuse me, this is wrong right here. Over the next year. Okay. Let's see. Oh, annual volatility. Okay. Annual volatility over the next half year. So it's just sigma equal to 0.5. Okay. Continuous compounded risk-free interest rate is 0%, and we assume there is no arbitrage in the Black-Scholes model holds. We are interested in a European call option on MGM with a strike of 15 and a maturity of 6 months. And what we want to do is ask the following questions again. What are phi of D1 and D2? And what is the Black-Scholes call price? Okay, so we start by writing down our inputs. Price of MGM Resorts today is $10. Okay, MGM has an annual volatility of 50%. Continuously compounded risk-free interest rate is 0. Assume there's no arbitrage, Black-Scholes model assumption holds, and we want to price a call option with a strike of K equal to 15 and maturity of 1/2 of a year. Okay. To price this call option, we use the Black-Scholes pricing formula. C0 equals S0 times phi of D1 minus present value of the strike times phi of D2, where D1 is equal to the natural log of S0 over K plus R plus 1/2 sigma squared times T over sigma root T. Okay, soon you'll have this memorized, no problem at all. D2 is equal to D1 minus sigma root T. Okay, we want to solve for the price of this call option. All it is simple plug and chug once we have all our inputs, okay, and a little use of Excel to calculate the phi's. We start in part 1 by calculating phi of D1 and D2. Before we can do this, we have to start inside out by calculating D1 and D2. So D1 is going to be log of S10 over K, 15, plus R, which is 0.00, plus 1/2 sigma squared, which is 1/2 squared, times 1/2 years, all over sigma, which is 0.5, times the square root of T. Let me load up my calculator right here, and I will calculate this out for us. So we have 10, 0, 0.5, 15, 1/2 year. Okay. We're going to see that D1 is equal to negative 0.97. Okay, and D2 then is equal to D1 minus sigma root T, negative 0.97 minus 1/2, which is the volatility, okay, times square root 1/2 which is equal to negative 1.324. Okay. We have D1 and D2. Now all we have to do is plug them into Excel to get phi of D1 and D2. Phi of D1 is norm.s.dist of D1, negative 0.97, comma, true. Plug this into Excel. What are you going to get? You're going to get this is equal to 0.1660. And phi of D2, doing the same exact thing. I'm not going to write it out here. I got very little space, but it's going to be equal to 0.0928. It's a good way to check your answer. Okay. In the second part now, what we have is that we have all the phi's. We just want to plug in K and S0 to get the call price. So in the second part of the problem now, we just plug everything in. The call price today is equal to the stock price times phi of D1, which is 0.1660, minus the present value of the strike, okay, times phi of D2, which is 0.0928. And what you're going to get out of this is that the call price is going to be right around 27 cents. Okay, so the call price is equal to C0 equal to $0.27. Again, Black-Scholes, very, very complex way to derive this equation, but the end result is elegant and simple, easy to use too. All you do is plug and chug. Okay. So the Black-Scholes model is definitely, undoubtedly, very mathematically beautiful. However, it also has a very nice, intuitive economic interpretation. And that interpretation is, of course, it's just the price of the replicating portfolio. To see this, notice or recall that the payoff to a call option, CT, is equal to the max of ST minus K and 0. Notice that you can rewrite this using two terms. The first is you take S0 and you multiply it by something called ST over S0, bracket ST greater than or equal to K. And then you subtract, okay, something called K, and bracket times 1, ST greater than or equal to K, where this bracket term, ST greater than or equal to K, is equal to 1 if ST greater than or equal to K, and 0 otherwise. Okay. The first term over here, okay, S0 times ST over S0 times this bracketed term, ST greater than or equal to K. It's just the payoff, okay? It's just S0 shares times the payoff of an option that pays the gross return, ST over S0, if ST greater than or equal to K, and 0 otherwise. And the second term is just K times the payoff to an option that pays 1 if ST greater than or equal to K, and 0 otherwise. Okay, so the formula says that a call payoff is equal to the payoff of a portfolio that's long S0 units of an option that pays the gross return if ST greater than or equal to K, and it's short K units of an option that pays 1 if ST greater than or equal to K. And the price of the Black-Scholes call option price turns out to be the price exactly of this replicating portfolio. Okay, the price of an option that pays the gross return of ST greater than or equal to K, we can show that it's equal to phi of D1. We can show also that the price of an option that pays 1 if ST greater than or equal to K is equal to phi of D2 times e to the negative RT. We won't do it in this class, but it can be shown. The replicating portfolio is just long S0 units of this first option, and it's short K units of the second option. And so to get the price of the call, you just take the price of the replicating portfolio, which is S0 times phi of D1 minus K times this phi of D2, e to the negative RT. It's just a simple application of the law of one price. It's just pricing these options, which Black-Scholes is good at. So that wraps up the second part of lecture 14. Let's take a quick break. When we return, we'll learn how to price puts in the Black-Scholes model, and we'll resume that in the second video.